All right, back from break. We're ready to move on to chapter 22. So a lot of stuff in chapter 21, not as much in 22. And of the stuff in 22, there are going to be a few items that are going to be very important to us, and others not so much. And so I'll try to point those out as we go along. Chapter 22 is called Gauss's law, and Gauss's law is it's a technique we can use to calculate electric fields. Now, what you know from our lectures in chapter 21 is that we've already been looking at different ways of kind of estimating electric fields and then carrying out calculations of electric fields. Gauss's law has a little different feel to it. And it's really, we'll take a look at examples where Gauss's law is useful. Anyway, I want to talk a little bit about this picture that we have right here for Gauss's law. What Gauss's law says that if I have a charged object, there's an object with charge Q right there, it's going to have a set of electric field lines. Is there a way I could look at the electric field lines and use that to calculate how much charge I've got? So first of all, the idea is, here's a charge. What if we surrounded the charge with an imaginary spherical surface and we counted all the electric field lines? That would be a way that we could back calculate and determine how much charge is inside the circle. Now, if I've got a spherical surface and I've got a point charge right at the center, then the electric field is going to have the very same value everywhere along the surface. So I move along the surface and I count all the electric field lines, and I'm using that as a way to, what I'm actually doing is I'm integrating the electric field along the surface. And the integration looks like this. Now, what happens when you draw that integration formula like this on the board, half the class says, yes, awesome, we get to try out some of that stuff we learned in math. And then half the class is panicked or maybe a little bit worried about where this is all headed. And I want to say, don't worry about this, give it a chance. It turns out the integrations that we do are fairly simple. In fact, if you want, you can avoid the integrations pretty much entirely. We'll see how that works. So the idea of carrying out this integration is to take the electric field at every location along the surface. Now the surface is being represented by little tiny pieces of area. The surface as a whole, if it's a spherical surface, then the spherical surface would have a surface area of 4 pi r squared, right? And so what I got to do is, if I were just integrating over the surface, I would get 4 pi r squared. But what I'm going to do is, instead, at each location, I'm going to take a little piece of area, multiply it by the electric field at that location. And then I'll move on to the next little piece of area, multiply by the electric field. Now remember, what we said is, if I can come up with a surface that has a lot of symmetry to it, then I can guarantee that the electric field will be a uniform value at all locations. And you guys know that if I have a constant inside the integration sign, the constant can be brought outside. So for all the examples we're going to be using Gauss's law, this integration allows us to bring out the electric field, and it just becomes electric field times the area. So for a sphere, for example, that would just be E times 4 pi r squared. So I don't have to do much with that integral other than just write down E times surface area. So what Gauss's law says, if I take the electric field at every location, multiply it by the surface area, that will tell me how much charge is enclosed. If there's more charge inside, the electric field will be larger. If there's 5 times as much charge, the electric field will be 5 times larger. Now, where is it that I have to draw this imaginary surface? And Gauss's law says, anywhere you want. It doesn't matter where you draw the surface. If, instead of drawing this big surface, I draw a smaller one, well, the area is going to be less, but the E field is going to be more. So if I draw a small surface, I still end up getting the same value for Q. Or if I draw a big surface, what if I draw a surface way out here? Remember the charge is in here. The integral is still E times 4 pi r squared. And the E field will be less, but the area will be larger, and the two effects completely balance out. That is working because the electric force drops off exactly like 1 over r squared. The surface area gets bigger by r squared, a factor of r squared, but the electric field drops off by exactly the same factor. So that allows us to use Gauss's law. Now, what would happen if I drew a surface that was crazy shaped? So let's say instead of drawing a nice symmetric surface to carry out the integration, I draw a crazy surface. Does Gauss's law still work? And it still works, but it's no longer useful, because carrying out the integration along that blue surface is going to be too complicated. It's not going to be a practical calculation. So, when is Gauss's law useful? When I've got a lot of symmetry. What's the very best symmetry we could work from? Spherical. Gauss's law gives us exact answers if we have spherically shaped charge distributions. So let's head on and see how this works. First of all, they want to introduce the idea of electric flux. They're going to say there's an electric field, and the surface is tipped. So if I've got an electric field passing through a surface, but the electric field is tipped, what do? Do I keep the entire electric field in my calculations, or just the perpendicular portion? And the answer is just the perpendicular component. And that's it. So what it says is, what happens in the case where the electric field is not directed perpendicular to the surface? Now, to keep track of that effect, we actually define an area vector. Now, maybe you've seen this in some calculus classes, maybe not, but we do make use of this in physics. It turns out if I have a surface area, and I want to write the formulas in terms of vectors and vector components, the vector used to represent an area, there's the area vector right there, see? Capital A, that's got to be it, area A. That vector has a magnitude, that is the area of the surface I'm looking at, and it has a direction defined to be perpendicular to the surface. Now that seems weird, right? You go, well, I have a surface here. Why is its vector oriented perpendicularly? And the reason why is mathematically, that is a unique direction. Let's think about this. If I have an area and I had a vector within the area itself, that wouldn't tell me how the area is oriented, right? It would take two vectors within the plane itself. But with one vector that's perpendicular to the surface, that uniquely defines how the plane is oriented. And mathematically it works. So by defining the area vector to be perpendicular to the surface, we can write down formulas in vector notation. So that's what we do. Now for us, the important thing to realize is when we're calculating electric flux, we're only going to include the electric field portion that is running perpendicular to the surface. If I have an electric field component running parallel along the surface, that doesn't count. And the reason why, it's going back to our first picture here, what Gauss's law is keeping track of is how many electric field lines cross the surface. Now, how many electric field lines are running along the surface? And so the dot product in there, see, there's the area vector, there's the electric field vector, and the dot product is making sure that we only keep the component that's perpendicular to the surface. And I'm going to say you probably don't even need to keep track of that in any of the problems. Let's see if any examples come up. In this example, they're showing how the dot product works. So they're explicitly taking the electric field times the area vector times cosine theta. Now they've given us a constant electric field, 200 newtons per coulomb. They've given us a constant angle, saying it's theta. So this electric field flux calculation, now for flux, the symbol that gets used is a capital phi with a little subscript e there, or a capital E. So this is the electric field, and this is considered to be flux. Flux is when we integrate a vector over a surface. So here's the electric field, here's the angle, the integration, everything comes outside, I can add all the area together, and it says, hey, the flux, if the electric field is constant, then the flux is given by E times A times the cosine of theta. That's telling us that we're just going to keep the cosine theta component, the component that's perpendicular to the surface. Putting all those numbers in, I'm able to go in and calculate a value for that. Okay, so that's an example of an electric flux calculation. Now, the way this works, so here are the area vectors. The area vectors are pointing directly out of these surfaces. And what happens is, the direction of the electric field will either cross into the surface, into the volume enclosed by the surface, or it will be passing outwards. Now, if the electric field is directed outward through the surface, that counts as positive flux. And electric field that's directed inwards counts as negative flux. Okay, and so Gauss's law is going to be useful if we can get a situation where there's a lot of symmetry. Let's try one of those situations. This is our favorite. There's a charge, and it's a point charge. And it's surrounded by a spherical surface. We're just imagining the spherical surface. It's not really there. But mathematically, we're going to imagine enclosing that charge, and we're going to make sure that the spherical shape of the surface is centered on the location where the charge is. And so what that means is that when the E field crosses any location on the surface, it's going to have the very same value. We're using a symmetry argument to say the electric field is a constant. So see how this, now this is going to impress your friends. You're going to say, your friends are going to say, what are you doing in physics class? And you're going to say, we're doing Gauss's law calculations of electric fields. And then you're going to show them this formula, and that's going to impress them. And you're going to know that the dot product can be removed, and then the electric field is constant. And so the electric field can be brought outside the integration. Now that little circle on the integral means that we have to integrate everywhere on the surface of a closed volume. So that surface area closes on itself, and so there's a volume inside that surface. And once we integrate that surface area, it's going to give us E times 4 pi r squared. Now from this, you can see how if we draw a smaller Gaussian surface or a larger one, values of little r could be different. Now how is that going to figure into our calculations? And the way that figures in is Gauss's law says that this flux calculation can be set equal to Q divided by epsilon naught. Now epsilon naught was one of our force constants. We're going to get this switched around here in just a minute. So Q over epsilon naught is equal then to E times 4 pi r squared. And when we solve for the electric field, it says the electric field surrounding a point charge is Q divided by 4 pi epsilon naught divided by the distance squared. And if you remember, 4 pi epsilon naught 1 over 4 pi epsilon naught is the same thing as little k. So what we've done here is we've used Gauss's law to solve for the electric field of a point charge. Now, the electric field is dropping off. Let's go back and look at this. The electric field drops off exactly like 1 over r squared. The surface area is increasing exactly like r squared. So E times the area is a constant. It doesn't matter where we draw the Gaussian surface. We do want to make sure the Gaussian surfaces are drawn so that the symmetry is maintained. We had a point charge, and so a sphere surrounding that point charge maintains that symmetry. So that's an example of using Gauss's law. Now, like that first picture at the beginning of the chapter when we first started out shows, this is going to be true regardless of where we draw the surface. Now, the left side of the calculation is going to be easy if we pick a symmetric surface. If we pick a surface like blue, forget it, I'm not going to do that calculation. Okay, so we can relate the total enclosed charge to the electric field flux that we calculate. And that's how Gauss's law works. It's kind of the basis. So let's look at a couple of examples here too. Let's say that we have 2 spherical surfaces that we've defined. They're the very same spherical surfaces. There is a charge inside one of them, but there isn't any charge inside the other one. If we do a Gauss's law calculation with this surface, what will we get? And what we'll find out is the flux works out to be proportional to the enclosed charge. For this surface, all of the electric field lines are exiting across that surface. That's going to give us a value on the integration proportional to Q. But what happens over here, that volume does not have any enclosed charge. What happens if I carry out a flux calculation? Well, on this one, every electric field line that enters the volume eventually leaves. And that's an indication that there is no net charge enclosed in that volume. I can count all the electric field lines going in, I can count all the electric field lines leaving, it adds up to be 0. So when we carry out that flux calculation, it's 0, and the 0 tells us there's no net charge inside. So that's why Gauss's law works. Now, where Gauss's law becomes really useful, let's look at a spherical shape of a charge. Now they're saying it's a conductor. It doesn't have to be a conductor. It could be an insulator. The important feature here is that we have a spherically symmetric distribution of charge. So we have this charge set up on this surface. It uniformly distributes itself because it's a conductor. It uniformly distributes itself because it's spherically symmetric, not because it's a conductor. But it's able to arrange itself however it wants because it's a conductor. We could just as easily make this out of an insulating material, and then we would have to make sure that we built into that spherical shaped material a uniform amount of positive charge everywhere. Okay, and in any case, we have a spherical distribution of charge. Now, if you think back, we don't really have a technique from chapter 1 to solve for this, except if I picked a point right here, I could integrate over this charge distribution. Now that would be a terrifying integral to carry out, because a little bit of charge here is a certain distance away from this point, right? I want to know what the electric field is right there. I would have to do some pretty complicated calculations and keep track of all the different vector distances in order to do that calculation. What Gauss's law says is, all right, the direct integration techniques are going to be really difficult, so instead we'll use Gauss's law. what we'll do is we'll use the symmetry of the distribution to argue that if I surround this with one of my imaginary Gaussian surfaces, the electric field at every location will have the same value. What that means is that I can carry out a flux calculation of electric field times the area and relate that to the charge enclosed. Now the electric field is going to be non-zero outside here. We can calculate what the electric field is. What will the electric field inside be? And Gauss's law says it's going to be zero. And here's why. Any Gaussian surface that I draw inside here, by symmetry, the electric field has to have the same value everywhere. Well, since there are no electric field lines anywhere, there is no flux and there's no electric field, so the electric field is zero. Now, at first you might think, well, sure, the electric field is going to be zero right at the center because there's going to be perfect cancellation, and you'd be correct. The electric field is zero at the center because if I'm right at the center, the electric field from here exactly cancels the electric field here. But Gauss's law is making a stronger statement than that. Gauss's law is saying any location inside here, the electric field will be zero. I will get perfect cancellation at any location. And you might be saying, well, how is that possible? If I pick a point right there, how is it that I'm guaranteed that these charges and these charges over here will have exactly opposite effects? And that's because if I look at the distances to the different parts of the sphere, the areas where I'm closer in, the electric field effect will be larger. So, for example, let's take the contributions from this sector and compare them with this sector over here at this point. So I'm much closer over here, but the electric field is stronger, but it's a smaller area. If I take this sector and I match it on the other side, I'm not just going to get the contributions from here, I will get the contributions from many sectors. And so what happens is that the two effects from the two different directions exactly balance out. And the reason why is that the electric force works exactly as 1 over r squared. Again, it's another test that the electric force behaves like 1 over r squared. If it didn't, Gauss's law wouldn't work. All right, so let's set this up using Gauss's law. Let's go outside the sphere first of all. So Gauss's law has this really cool looking integral, which we said is going to reduce down to E times surface area. It's the electric field integrated along the surface area of that sphere. And again, that's just going to simplify to E times 4 pi r squared. So the left side becomes E times the surface area, and the right side is 4 pi k cubed. The 4 pi's cancel. I can solve for E. E becomes kq over r squared. So this is important. It says, we've already looked at point charges, and we've just kind of said, okay, for point charges, the electric field is just given by kq over r squared. But what Gauss's law is saying, not only is that true for any point charge, that formula also works as long as I am outside any spherically symmetric distribution of charge. It doesn't have to be charge concentrated at one point. It could be any series of spherical shells that are charged, or it could be an entire sphere that has been charged. So that's extending our formula so that it works in many more circumstances than what we showed in chapter 21. Now what happens inside this distribution, and as we were saying, we can So here's Gauss's law. We can write it this way, which is how I'm going to write it. The textbook is going to write it this way. And remember, epsilon naught is equivalent to 1 over 4 pi k. I'm going to stick with little k all the way through, but again, from time to time, we'll come back and remind ourselves what the epsilon naught, how that's related to little k. On this example, the q that's enclosed, if I'm inside, the Gaussian surface that I've drawn inside that includes point B, it doesn't enclose any charge at all. So since the enclosed charge is equal to 0, that's what this is right here. Ooh, that needs to say enclosed on it too. I should have a little arrow there and an explanation saying that charge is the enclosed charge, the charge that's inside the Gaussian surface. So the surface we've drawn outside encloses all of the charge. The Gaussian surface we've drawn inside encloses none. And that says everywhere outside the surface, kq over r squared. Everywhere inside is 0. So the electric field drops immediately to 0 if all of the charge that we have here is on the surface. If that's charge that's all on a surface, once I cross that surface and go inside, the electric field will drop to 0. What would happen if we have, what happens if we have a sphere where the charge is not all on the surface? What if it's uniform all the way through? Well, it's not going to have any effect on my Gauss's law calculation outside. So very quickly, we can say the electric field outside is still kq over r squared. But this will make a difference for the electric field inside. Right at the center, we can still make the argument that all the electric fields will exactly cancel each other. These electric fields are vectors, and so they can cancel out. Right at the center. But these other regions are going to have electric fields, and we can calculate that by calculating out how much charge is enclosed in surface 2. So let's see what this one looks like. Again, outside, if I'm looking outside the sphere, the q enclosed is the entire q. If I'm looking, is the entire q. When I carry out this integration, it's going to be e times 4 pi r squared, where little r is bigger than the radius of the sphere. So right now we're looking at point A being outside, and then later on we'll move it inside. I guess I didn't write point B. I needed to write point B on here. So the E field times that surface area is 4 pi k times q, and I'm getting my old familiar formula for outside a spherical distribution of charge as being kq over little r squared. Now inside things get more complicated. I'm going to use the very same formula where q is the q enclosed, but q enclosed now is not the total charge. As I move closer and closer to the center with my Gaussian surface, I will be enclosing a smaller and smaller portion of the charge. So I've got to get an expression that tells me, as a function of little r, how much of the charge have we enclosed. Now to get this, I'm going to take the total charge, and then I'm going to multiply that by the volume enclosed divided by the total volume. This is going to be some ratio, and that's going to tell me how much, what fraction of the total volume has been enclosed, because we assume the charge is uniformly distributed. So if I can get a ratio of the volume enclosed to total, I can get an expression for the enclosed charge. Now when I do that, the volume of a sphere is 4/3 pi r cubed divided by 4/3 pi big R cubed is the volume of the entire sphere. Little r now is inside. So I'm using little r to represent regions outside, and I can use little r to represent regions inside. So now it's point B inside, and now little r is smaller than big R, and that's the fraction that's enclosed. So I'm going to use Gauss's law. The left side turns out to be the easy side of the equation, right? When you look at that integration, you go, oh my gosh, how am I going to ever do that integral? Every problem we do using Gauss's law, this integral reduces down to E times the surface area. We can just immediately go from here to here. This is the most difficult part of the calculation, is determining how much charge we've enclosed. In this case, it's Q times little r to the third over big R. So I'm going to substitute that in. And then I'm going to carry out the calculations. The 4 pi's canceled. The electric field then is given by kq over little r squared, same as before. Oh, but there's an extra factor of r to the third over big R to the third. That has to be included in this. So the electric field inside is going to be the electric field outside times that stuff inside the parentheses. And that says that the electric field then, I'm going to move some stuff around to try to explain how you could possibly think about this. I'm going to move 2 factors of big R here. I'm going to get some cancellation going on here. I'm going to write this as kq over r squared. Now, what is kq over r squared? Big R squared. That's the electric field at the surface. Right at the surface, that formula is going to be kq over big R squared. If I go inside, I'm going to take that surface value and it's going to drop off linearly. It's going to drop off like a straight line formula. And the factor here is r over big R. And at the center, that's still going to go to 0. So at the center, I will still have perfect cancellation of 0. But as I move, okay, so let's take a walk. So I'm going to start right at the center, measure the electric field. Sure enough, it's 0. And then I'm going to start walking along this path. My intention is just to keep walking through the entire sphere and then out away from the sphere, and then do a series of electric field measurements and see if they line up with my formulas, and they do. And so what I find when I'm measuring the electric field is, look, it's increasing linearly as I approach the surface. Right at the surface, the electric field value is going to be this. It's going to be K big Q over big R squared, right at the surface. I should have written that in too. Right there on my E field, right at that location is the KQ over big R squared. And then I stop using that equation, and once I'm outside, I start using this one. So inside, it has been increasing linearly with the distance r. Outside, it's going to drop off like 1 over r squared. And the crossover between that is where we run out of charge, right? Once we head outside of this, we're no longer accumulating more and more charge, but we are getting farther and farther away. Okay. So, the electric field at every location involving a spherical distribution of charge. That's it. A uniform, spherically uniform distribution of charge. So this is something this would be, by direct integration with Chapter 21 methods, this would be a horrendous problem to carry out. With Gauss's law, not such a big deal. Now, spheres work really, 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 really well. There's a couple of other shapes that we use Gauss's law for. These are just approximate. And I always feel like textbooks kind of overstate how useful Gauss's law is here. So let's take a look at some of these. Here is a charged stick. Now you might think this is like a wire with current in it, but it's not. If I have a wire with current in it, the wire doesn't become charged. Okay, the current just keeps moving, but no regions of that become positive or negative significantly. So this is actually an object that has been charged. So it can be an insulator or a conductor or whatever. Let's say it's an insulator, and we've built this material, and it's all charged, but it's kind of one-dimensional in shape rather than spherical. Well, just by thinking about electric fields, what we're guessing is that the electric fields are going to be directed away from the charge, except on the ends. So when I wrap around the ends, the E fields have to wrap around. Now, Gauss's law is not going to be very good at calculating what the E fields are in these complicated regions. Where Gauss's law is going to work as a reasonable approximation is in the center regions, not very far away from the wire. If I can stand at a location near the wire where I look and it looks like the wire's going on forever and it looks like the wire's going on forever and it's charged, that gives me a lot of symmetry. If I'm in that region, then the argument I make is the E field must be directed perpendicular away from the surface of the wire, and that allows us to bring in Gauss's law. So Gauss's law, where is it? Oh, there it is. Now remember, the Q's here are always Q enclosed. I should just really write that out. So let's say that we have a certain amount of Q enclosed in a certain length, so that we have a charge per length given by Q divided by L. And we use lambda for that. That shows up from time to time in the examples in the book. So that's a charge per length. Now I'm going to take Gauss's law. We said the left side's easy. It's the electric field times the area that the electric field is crossing. Now what we're assuming with this cylindrical symmetry is that the electric field only comes away from the wire. That means that the electric field doesn't pass through the end plates, right? I've got this Gaussian surface. It's cylindrical in shape, but the only place I'm getting flux is along the curved portion. I'm not getting it out the ends. So when I do the area, I'm going to do the surface area of the curved portion of a cylinder. Now, cylinder, if it's got a, I've got it. So little r is the radius of my Gaussian cylinder, and so the Gaussian surface will have a surface area of 2 pi r, that's all the way around, and then the length of the cylinder. So that is an area. It's not as easy as the sphere surface area, but when you stop and think about it, you just have to be familiar with the surface area of a cylinder. And then I can set that equal to 4 pi kq, where q is the enclosed charge. That gives me an electric field that is 2kq over L times 1 over R. And then the q over L, if I want, I could rewrite that as lambda. So again, two different versions here. I could write it in terms of the total charge, or I could write it in terms of the charge per length. Now, how good of an approximation is that? The Gauss's law approximation will work well if the distance I am from the line of charge, the little r value, is very small compared with the length of the stick of charge. So I've got this really, really long stick of charge, and I have to stay very close to it. Otherwise, that's not going to be a very good approximation. Okay, and so let me repeat that. What's going to happen is that the electric field lines will begin to spread out. This charge is not infinitely long. And so when I'm really close, the electric field is as if it's infinitely long, but once I get out here, I can see the ends, and I can see that the electric field is beginning to diverge. In fact, if I get far enough away from this line of charge, what does it look like? Looks like a point charge if I get far enough away. All right. Okay, one last example. Let's see. With shapes of charge distributions, what if we had a surface just covered with charge? Could I use Gauss's law for that? Now, these always get represented as like squares, but let's not think of it as a square. Let's think of it as a disk. In fact, if you remember, back in chapter 21, we did a direct integration of the electric field along the axis of a charged disk. So we did that problem exactly through direct integration. And now what we're going to do is we're going to use a Gauss's law approximation for that. And the way it works is this. Let's take this, a circular region, and let's call that area A. And what we're going to say is that for that circular region, we're going to consider the electric field. So these are electric fields out here. Man, that needs to get written in too. So I've got electric fields out here. Now the areas that we're going to take a look at the electric field, I'm going to have electric field passing through this area on the end here. And then I'm going to have an electric field pass through this area also. If I turn this disk sideways, what it looks like is I have a bunch of charge on this disk, and the electric fields are directed away. And what we're asking is, what is the electric field then at some location over here? Now this time, instead of a charge per length, what's more useful is a charge per area. So how densely placed is the charge on that disk? And for that we're going to use sigma, that's the convention, and that's the charge divided by the area of the disk. So again, this thing is charged. I should draw some plus signs in there. I did draw some plus signs here. Now when I carry out the integration here, I'm going to get the electric field and then just multiply it by the areas of those two end plates. Now I could write that as pi r squared, but instead I'm just going to leave it as two areas. So there's an area of integration from the electric field directed this way, and there's an area over here too. And so what that leaves us with is that when we carry out this calculus, we've enclosed charge Q, we're going to get an electric field then that is 2 pi k times the charge enclosed divided by the surface area on just one side of that disk. All right, so since I've got Q over A, this is where I was headed with this. Oh, I wrote that as pi a squared. So this is just going to say for any shaped disk, for any shaped flat surface of charge, I can take Q over A, and that's the formula. Now, that's considered to be the formula for the electric field right along an infinite sheet of charge. So the charge just goes on and on and on. If I've got a disk, now in reality, charge distributions don't go on forever. They're not infinite. And so that's why back in chapter 21, we took a look at this example to see what it would look like. And this was the finite calculation. We did a finite disk, gives us this formula. Well, when we looked at that formula that we calculated back in chapter 21, what we found was right at the surface, the electric field was 2 pi k over sigma, right at the surface, but then it dropped off very rapidly. In fact, we found that by the time we were at a distance of just 1a, it had dropped down to under 30% of its surface value. And then by the time we're at 2a, now that would be a diameter, it had dropped down, it's down to about 10%. So what happens in these chapters on Gauss's law, I always feel like they're trying to get students to be really enthusiastic about how great these Gauss's law approximations are, when in reality, they only work. They work perfectly if you have spherical distributions, but if you have these sheets or cylinders, they only work if you're really close to that surface. And so the Gauss's law approximation says that the E field is a constant outside of this disk of charge, but we know it's not. In fact, we know it drops off very rapidly. So the Gauss's law approximation says, you know, as approximation, I can treat this as being constant. Well, how far is that approximation good? I'm going to say not very far, right? By the time you've come out to here, you've dropped down to 90% of the electric field, and the distance you've traveled is 1/10 of a radius. So again, if you've got a disk with a certain radius to it, let's say the radius is 10 centimeters and the disk is 20 centimeters across, by the time you're 1 centimeter away from that 20 centimeter diameter disk, the electric field has already lost 10% of its value at that point. It's dropping off pretty quickly. So anyway, just a warning with these. When people say, go ahead and just use the Gauss's law approximation, say, that's only going to work if we're either spherically symmetric or if we're really, really close to the surface. Now, what we use this for is we say, all right, let's take a surface of a conductor. If I have a conductor, then I know that the electric field inside perfectly cancels out, and that says that the electric field then is only directed away from the surface of that conductor. So if I'm looking at the surface of a conductor, and the electric field is only going out in one of the directions, that's going to change my formulas. That's going to give me an electric field that is 4 pi k times sigma. It's not going to be 2, it's going to be a factor of 4 instead. Now, here is that example. And so what we're saying here is, here's the Gauss's law. And so what's happening is I have a certain amount of charge enclosed, but this time the electric field is only going out in one direction, so the left side integration becomes E times A is 4 pi k q, and so the electric field then is 4 pi k q over area, or 4 pi k times the area density. Okay, so how do we make these two formulas agree with each other? Because I got one formula for this disk, where the electric field is going out in both sides, as 2 pi k times sigma. But then I have a conductor, and it says 4 pi k sigma. Well, the way this works is, if you're working with an insulating piece of material, they assume that the charge is somehow embedded in the material. So if I look across the area, the total charge is Q. But if it's a conductor, we think of the charge as only being on the surface. So if I'm talking about how much charge there is on the surface of a conductor, there's twice as much. I'm including two surfaces there. So for the conductor, I've got twice as much charge. To send the electric field off in both directions, it takes two sets of charge rather than just one, and that leaves me with a factor of 4. So it's just kind of a convention as to how we deal with electric fields from insulators and how we deal with electric fields from conductors. And that's really what it comes down to. Okay. Here's another. Let's take a look at a couple more examples, and then we'll actually wrap things up with chapter 22 today. We're getting very close to the end here. Here is a conductor, this funny shaped conductor, and then the conductor has a cavity inside. So there's this opening, and once again we have placed a point charge inside here. And this is a conceptual question. So supposedly we don't have to do any math on this. And so what we're going to do is draw a Gaussian surface here and say that we do have an electric field inside this conducting piece of material. Oh, this is all we've got to work with. Okay, what do we have to solve for then? Suppose it kind of... Oh, okay. So what it's saying is that we're going to end up with electric fields inside here. And we will draw... We looked at an example earlier that very much like this. Was it chapter 21 or chapter 22? So we did look at an example where we said the electric field lines, might have been chapter 21. We drew electric field lines and said that within the conductor there will be enough negative charge to offset the effect of the presence of the positive charge. So if we place a positive charge inside that conducting material, inside that cavity, that will result in a charge of minus Q on that inner surface. Now the conductor itself started out with a charge of plus Q already. So the conductor now has a charge of negative Q here. That's going to add an additional plus Q to the outer surface. So on the outer surface now, we're going to have a plus Q and the original plus big Q both that are going to be present on the outer surface. And they did not get that drawn in, did they? Okay. Yeah. Okay. Not so important. Not going to worry about that one. Maybe I will... you guys may see that drawn up in the slides. I may draw up a solution to that one and add that in. Okay. Again, we're getting pretty close to the end here. Here's an experiment that we can actually carry out to verify that the electric force behaves like 1 over r squared. What we've been saying with this chapter is Gauss's law works only if the electric force drops off exactly like 1 over r squared. So we could turn that around and say, well, this then would be a very sensitive technique that we could use. We could take a charged, so here's an insulator to isolate everything else, but this is conducting and this is conducting. So the material we have here, electrons can move back and forth freely, and the object that we're lowering inside also, the electrons can move back and forth freely. So I'm going to lower this inside. Now, I don't like this picture because it looks like I'm going to hit the sides when I come in. The idea is that I can bring this all the way in. I haven't touched the sides yet. I can close this off, and then I can allow this to make contact. Now, if what we've been talking about, Gauss's law, is true, then what should happen is all of the charge from this sphere should go to the outer surface. So I should be able to get 100% transfer of the charge away. Now what that means is I'll be left with, doesn't mean I won't have any protons or electrons left. It means that right now I'm missing some electrons. This thing is positively charged. I bring this in, it's missing some of its electrons, it doesn't have enough to balance out the protons. When I touch this surface, exactly enough electrons will transfer into this until it becomes electrically neutral, and then the transfer will stop because of the nature of the electric force. What will happen is that since the electrons have been drawn from this surrounding material, now that surrounding material will have missing electrons, and the depletion of electrons will show up along the outer surface. So we could set up an experiment like this. People have done this. It's a very sensitive experiment that's done. We can drop this charged object inside. It becomes electrically neutral, assuming that the electric force behaves like 1 over r squared exactly, so that when we pull this outside, again, making no contact with the conductor, we bring the object out and measure that it no longer has any charge at all. The charge has been brought right to zero. The transfer of electrons has been just enough to bring this charge to exactly 0, and the amount of electrons that have transferred have left. Whatever charge this came up in with is now the total charge of that surrounding enclosure. Okay, so anyway, we'll end things right there. So that's chapter 22. Again, I'm going to say the most important items here. Take a look at those examples with spherical distributions. Those are really handy because it really does allow us to go in and let's say we have a spherical distribution of negative charge, which we do when we're looking at electrons in atoms and molecules. We can actually determine what the electric field would be inside the electron distribution of an atom or a molecule. Okay, so there are examples where we want to be able to go in and use those approximations. Also take a look at the cylindrical symmetries and the planar symmetries. I think there's a homework problem, 1 or 2 for each of those, but I think you'll find the bulk of the homework is concentrated on thinking about spherical distributions of charges and their electric fields. If you guys have questions, stop by.